Comment that came in class, some people have been confused by articles in the news about ozone being a greenhouse gas. Now, as I've taught this course, you may not remember this, but when we started talking about ozone and carbon dioxide, I actually said something like the following, that the worry about the greenhouse effect comes from the burning of fossil fuels and the carbon dioxide that goes into the atmosphere. The carbon dioxide isn't really enough to cause it much by itself, but if it raises the temperature a little bit, then there's a worry that there'll be more evaporation from water, and that this water will then actually amplify the effect, assuming it doesn't form clouds that then reflect the sunlight. And that's not really known, which is why this whole issue is still somewhat controversial. So I want you to think, and I want you to remember always, that CO2 is responsible for the danger of greenhouse warming. CO2 comes from fossil fuels. Now, there are other gases that contribute. CO2 isn't the only one. I mentioned water vapor. That's clearly very important. Creating water vapor ourselves does not seem to be a big issue right now. It may be someday. The real issue, the social issue, the international issue is creating carbon dioxide, putting that into the atmosphere. There are other greenhouse gases too. Methane is a greenhouse gas, and it turns out so is ozone. And people are worrying about these little effects. And when I first taught this, I tried to make a point that I don't want you to be confused by this. For this purpose of this class, the greenhouse gas is carbon dioxide with a water vapor amplification. Okay? And yes, ozone contributes a little, but I want you to know that ozone, the primary interest in ozone, it comes about because of its potential destruction of its potential destruction in the ozone layer. Destruction by CFCs, like Freon, chlorofluorocarbons. The creation of the ozone hole over Antarctica was an example where we now believe that human chemicals introduced into the atmosphere quite inadvertently, mostly disposing refrigerators and old air conditioners that use these CFCs, that was actually destroying ozone above Antarctica. Not that ozone destroying over there led to any deaths of any kind of animals, but it indicated that we are really having an effect on the atmosphere that, in a way that was unpredicted, and that means we have entered the dangerous realm where we are affecting things that can truly affect our health that are unexpected. So we banned CFCs. It's been a successful ban, and people are not worried about destruction of the ozone layer from CFCs anymore, as long as the ban holds. So I want you to think ozone, CFCs, Freon, ozone hole Antarctica. True, ozone is a minor greenhouse gas, but not for the purposes of this course, because I want you to, sometimes small effects can be confusing. It's okay if you know that it's a small effect, but I don't want you in an essay to say, ozone is known because it's a greenhouse gas. If you say it's a minor greenhouse gas, the big one is carbon dioxide with amplified from water vapor, that's different. Okay. Last time people have asked me, well, I described a Xerox machine in which way that you would get a negative. How do you get a positive? The way that's done is, remember what happens in the Xerox machine? You have this drum. The drum gets the picture projected on it, like the film of a camera. But now you want to record it electronically first in order to turn it into a picture. So the drum uses the photoelectric effect. The fact that if, green light, and by the way, you notice the old Xerox machines, they used to have these green lights. I don't know if they don't use them anymore now. They have much more white lights. The old Xerox machines used to be very insensitive to certain colors like red because they use green lights, but they use green lights because that's the part of the spectrum that the eye is most sensitive to. The light from the Xerox, the light on the image will knock electrons off. That'll leave behind positive charges wherever light hit. Okay? But there's another way you could do it. And this is the way it's done in most modern machines. It's one additional step. That additional step is taken so you get a positive picture. So let me just go through that very briefly. You have this drum. The fact that it's round is irrelevant. They just do that so they can have one sheet of paper go through after another. And they put the image on the drum, not on a flat piece of film. So you have a light shining on the drum, and here's this picture. The drum, before it was exposed, was sprayed with electrons. So it was a charged drum. So, here's the drum. Here's the flat sheet where you put your your image. Here's the lens. And then the light then forms an image on this drum. There's an image here. Light basically, forms an image on the drum. However, on its way to coming over there, there were electron emitters that charged up this drum, so it was negatively charged. Now, the light shines on this, and the photoelectric effect. This was actually a really important thing 100 years ago, the photoelectric effect. It was a mystery because you shine light on the surface and an electron pops out. But basically, when you correct for minor absorptions and so on, it turns out the electron always comes out with the same energy. Think about that. You shine light, and the electron always comes out with the same energy. That was a real puzzle 100 years ago. We now understand it. I mean, if you have an electromagnetic wave, it's shaking these electrons. And you think sometimes they pick up a lot of energy and sometimes they pick up just a little bit of energy. But that's not what happened. When they shone the light on it, the electrons always came out with essentially the same energy. And it was Einstein who offered the solution. And with this was the creation of quantum mechanics. He said the light is shining, it has a certain frequency. The light is always absorbed with an energy equal to this constant times the frequency. And he suggested this, and it was the birth of quantum mechanics, quantum physics. I keep on calling it quantum mechanics because that's what a course here at UC Berkeley is called. But quantum mechanics, it's the old term. Quantum physics, it really covers waves, classical mechanics, just about everything. So I prefer quantum physics. So Einstein proposed this. Sometimes it's called the Einstein equation. Some people say, oh, Einstein never believed in quantum mechanics. He was the creator of quantum mechanics. There were aspects of quantum mechanics he was very uncomfortable with, especially the interpretation of the particle wave. We'll get to that. If not at the end of this lecture, then certainly in the next lecture. By the way, there's no reading due this Thursday. Okay? It's time to get going on the midterm exam. The exam's a week from Thursday. Instead of doing your reading for Thursday, do your rereading for Thursday. Reread those chapters. It's a good way to study. Reread those chapters and, reading them for the second time, or third, or whatever. Get into them. So, when Einstein wrote this paper, and a lot of people don't know this, but it was for this paper that he got his Nobel Prize. It wasn't for relativity. He invented quantum mechanics. So the Einstein equation, basically what he said was the energy in a wave can only be absorbed in certain quanta. That means in certain bundles. For a given frequency, the bundles are always this value. You could absorb 2 or 3 of them, but you can't absorb a half. There's no in-between. It's another version of energy gap, I guess. You could absorb 1, 2, 3 of these quanta. The electron could come out with a certain amount of energy. It could absorb 2 of them, but that turns out to be very improbable. So in principle, it could come out with twice the energy. But they all came out with the same energy. This photoelectric effect was a real mystery. The basics of the photoelectric effect is what we use today in the Xerox machine, in digital cameras, and in solar cells. So I want you to know this term, photoelectric effect. Maybe photoelectric. Photo, because it's the photon, it's the light that's coming in. Photograph is coming in. The light is coming in, knocks out an electron. And it's a key element in many of these technologies, including night vision scopes. So in the Xerox machine, they first charge this up. Then the drum comes, and where the light hits, it knocks the electron off. So when you're left over here, the dark areas still have electrons. The places that were bright have none. And then other dark areas still have electrons on it. Next, what you do is you put this in a smoke-filled room. Basically, lots of little smoke particles in the gas here. They're attracted to where the electrons are. So the dark regions get this dark stuff on them. Finally, you come over here and you rub this against a piece of paper. So as this rolls around, the paper comes around, and the dust sticks to the paper. They'll have a brush over here to clean this off, so this is clean for the next time around. If that doesn't work very well, if your brush gets dirty, then you'll have some of the previous image left over here. Your Xerox machines will always have, typically they have wires here, which are very sharp things with very strong electric fields, and those emit electrons that charge it up. It comes off here in the paper, and the last step is, now that you have this smudgy paper, you heat it up so that this stuff is called a toner. The toner is basically the powder, which is basically blown into this region to form a powdery gas that then sticks to where the charge is. And then the black parts stick to the paper, indicating the place where there's no light. Where there was light, there's no powder sticking to the paper, so you get the white of the paper. That's the image. Last thing you do is you heat the paper very briefly, just so that the glue or the wax or whatever is in this toner will melt, and it will fix it to the paper. So that's how a Xerox machine works. But the physics aspect of it is the photoelectric effect, basically quantum mechanical effect, the effect that was seen for that gave rise to quantum mechanics. It's a great story, by the way, how quantum mechanics came about, because when Einstein introduced this number, it wasn't his number. It was Planck's number. And this thing was called Planck's constant. And Planck had invented this number for a totally different reason, having to do with understanding the emission of light when you heat something. So it's a great story, but I'm not going to go into that story because you have too many important things to know, and digressing into history, we don't really have time. Question? How does a color copier work? Color copier, typically what you need to do is to put in a filter here, for example, so only the green light comes through. Then, if you have a flag, or let's say red, green, or blue, red, green, or blue. You do 3 of them. Now you could do this in several ways. You could take the light and break it up into 3 parts, so the red, green, make 3 different images, and some Xerox machines do this. And then the toner has to be green toner. So only the green light that's coming through. If your object is red, no light will come through. Okay? And then there you may want to, I mean, there are tricks here about whether you want to use a negative or a positive. I don't want to get into the real detail. Yeah?
I thought you would use CMYK.
Yeah, you could use either. Well, if you make little dots, they don't have to be CMYK. Anyway, I don't want to get into distracting details. The basic thing is you got to do the Xerox 3 times. 1 for each of your colors. And that's really the trick to color Xerox. Color Xerox has been rather slow to come about. Most color printing these days isn't done by the Xerox. It's done with inkjet printers. This was an amazing transformation to see inkjet printers really take over. But when I do my color prints now, it's almost all with inkjet printers, in which the image is stored in the computer. You measure how much red, green, and blue there is. That's done on the CCD chip. I'll talk about that in a moment. And then, as the paper goes by, there are the red, well, cyan, magenta, yellow, or red, green, and blue things that spray little dots on the paper. with the right colors. And that's a much simpler mechanism than the color Xerox machine, but still a lot of people do use the color Xerox machines. But it's basically 3 images that then have to be put together. Let me talk about the CCD camera. This is also based on the photoelectric effect, but combining it with something else from quantum mechanics, which is the energy gap you get in a crystal. I talked about this last time. Remember, we have spectral lines because the electrons are waves. They can travel in this orbit or this orbit. Those have different energies. They can't travel in between. There's an energy gap. They have to go from one to the other. In a crystal, electrons don't go in circles, but they do bounce back and forth. And when they bounce back and forth, they can interfere. And this gives rise to what are called energy bands. So typically, these are drawn. We have a crystal here. And you might think I'm drawing this as a picture where this is up and this is sideways. But I'm not. So this is an abstraction. And I'm not going to ask you to reproduce this on any exam. I'll tell you at the end which parts of it I want you to know. So you can relax and look at this. And it's easily misunderstood and confused. So listen carefully. Not that it's important for you to listen carefully, because I'm not going to require that you really understand this. If this is position, typically we plot here not height, but we plot the energy of the electron. So an electron that's here could have this much energy, or it could have this much energy. Now, in crystals, when you work out the math of these things bouncing back and forth, it was first done by Brillouin, I believe, there's this remarkable result that the energies that are allowed, it could have different positions too. It could be there or there or there. Could be there or there. These are different energies at the same position. Okay? And it turns out that you can have any position or any energy in this whole realm. But this energy right here, where there's no dot, you cannot have, because the waves tend to cancel themselves. So here's another band of allowed energies. These things are typically called forbidden. It means if you try to put an electron there, it would cancel itself out, so the result is you can't put it there. There means at this position with this energy. These energy bands are the key quantum physics that gives rise or is used in solar cells, used in CCD cameras, digital cameras, used in transistors, used in integrated circuits, used in computer chips. This is the key physics. It's not circular things like we had, with spectral lines. It's spectral bands. Here, you can have this energy or this energy. The energies are pretty close. You can have a particle come here and gain a little bit of energy. But it can't be here and gain a little bit of energy. It has to gain a lot. There's a gap. This is the energy gap. So I didn't derive this for you. I just gave you a plausibility argument that there will be some energies that are forbidden because the bouncing back and forth will tend to cancel. It turns out to give rise to gaps, and these things are called bands. This is an energy band. And you could have a few electrons in each band, or you could have lots of electrons in each band. So now, what I'm going to do is use this to explain how this is used in all these various technologies. And whether you remember how it works or not, that's icing on the cake. That's not as important. What you do need to know is that in a crystal is a regular array, it's a solid. In this crystalline solid, there is an energy gap. Now, typically, as used in many of these technologies, there are lots of electrons in this band. In fact, even though I say you could change by a little bit, typically this band will be filled or nearly filled. What that means is you can't have two electrons in the same location with the same energy, only one. This is sometimes called the Pauli exclusion principle. I'm not sure. I require you to know that. Which means no two electrons in the same particle wave. That means in the same energy, same location. They can't have, if you have a particle wave, you can't have two of them there at the same time. You have it or you don't have it. If you have it, it's called an electron. If you don't have it, then it's empty space. You've probably learned this in elementary school. You can't have two electrons in the same place at the same time. That's not quite true. They just can't have the same energy. Can't be in the same state. So again, I'm not going to try to teach you the rules of when electrons can be in the same state and when they can't. I'm just going to invoke them, and I'll try to be clear about what it is about this I want you to know. So what they do in this band is they put in so many electrons that they are basically all filled. Now, an interesting thing happens when they're filled. When they're filled, this becomes what's called an insulator. That is, you put an electric field over there, and this electron wants to move, but there's no place it can go, because the electron next to it is right there. I made an analogy last time. If I asked you all to move over one seat, and we were completely filled, you wouldn't be able to move over until someone else moved over. But they can't move over until the next person does. So this basically, if you put an electric field across this, normally you'd expect the electrons to move, but they don't because there's no place for them to move. When that happens, we call it an insulator. There are lots of things when you put electric, and put them across a battery, no electricity flows because they're insulators. Why not if they're full of electrons? Well, if it's a crystal like this, the electrons just basically can't move. Up here, there may be very few of them. And in two of the technologies, and several of the technologies I'm about to describe, basically solar cells and also digital cameras, this is basically left empty. Now, here we have the photoelectric effect. Okay, so what have I just described? We've described a gap. Electrons here that can't move, lots of space up here where they could move if they could get there. Now we get to the photoelectric effect. Suppose you shine light on this. This could be a solar cell, or it could be, now I have the light coming down. I shouldn't do that because this is not up. This is energy. So let me not confuse you with that. Let me shine light on this thing. Okay? And it could hit electrons up here if there were any, but there aren't. Could hit electrons here, and there are lots of them down there. Now, when the light hits it, just like the photoelectric effect in the Xerox machine, light hits it, they pick up a boom of energy. If the energy is enough, if the energy H times F is enough, then that electron is basically given more energy. If it's given enough energy to overcome the gap, then that electron could be at the same location. See, right here, this is the position. Same location, but it has a higher energy now. Can't get this much, this much, this much, or this much, but yes, it can get that much. Now, it's in this empty band. If there's an electric field across it, the electron can be part of the current. Your insulator has suddenly become a conductor because it's been hit by light. The more light that hits it, the more electrons there are, the more current that flows. You have a way of detecting light. Well, even better than that, if you don't put an electric field over here, these things get knocked up. You start having a large number of electrons up here. They start repelling each other. Not only do they repel each other, but they can move because there's plenty of elbow space up here. And so this becomes a solar cell. Want to wake him up? Yep. Please. Wake up. Don't want to miss this. It's not easy to understand from the text. It's important. This is how a solar cell works. I'm not going to review what I just said with emphasis on what I want you to understand. To make a solar cell work, you take a material that's typically a crystal. You use a crystal because the crystal has this band structure. And the most typical crystal these days is silicon. And so silicon is used. It's very cheap, but you have to make very pure crystals. I didn't explain why you needed pure crystals, but it's what makes it a little bit tricky. That's why silicon valley got its name, because they make these things out of the silicon because it has this nice band structure. Silicon is sometimes called a semiconductor. And that's because under certain conditions you can conduct electricity. So let me get back to where we are now. So here we have our silicon crystal. You have this band all filled with electrons, and because it's all filled, you can't have electricity flowing. When light comes in, it can give the electron enough energy so it overcomes the gap, gets up into this thing here, which is called the conduction band. And then electricity can flow. Here's the essence. Silicon has bands of energy allowed. There's a gap. Light coming in can take an electron away from the insulating region up into the conduction band. When the electron's in the conduction band, now electricity will flow. You could use this either to create electricity. That's what a solar cell does. You take this stuff, you put it out there in the sunlight, get these electrons accumulated, you let them flow, and you know, drive your electric motor. Or you put something like this in your camera. You have a large number of them in your camera. Maybe 3 million of them. Maybe 1 million, maybe 8 million, or 12 million. Each one on the back of the camera. So here's the camera. Cameras look weird these days. You ever notice that? It's as if it's okay now to make a weird-looking camera. In fact, it's like the Prius. You know, when they made the Prius, they decided to make it look weird so that people would know you had a Prius. They can't miss it. They did that with the Edsel, and it was a complete flop back in the 50s. But for the Prius, and then Toyota, Honda also made a hybrid automobile. But they made theirs look identical, so you can get a hybrid without anybody knowing it. So these were the two marketing approaches. This is my own analysis here. Honda said, no, you can get a hybrid, and you don't even have to tell anybody. Toyota said, oh, you can get a hybrid, and you will show off that you have a hybrid. And they were guessing different things, and at least in Berkeley, I'm amazed how many people, you know, think I'm a great guy just because I bought a Prius. I don't know if that's true elsewhere. Most Priuses sold of any auto dealer in the United States, I'm told, is in Berkeley. Okay, so here's our camera. And the camera these days look weird. I don't know. Digital camera. It may be inside of your, actually, you may have a digital camera that looks like this, with a lens in there, and then a mirror. And then down here, they put the imaging device. So the light comes in, bounces, and you form your image down here. It gets really thin cameras. Or they could have a lens here and a really short focal length and put the detector here. Now, the detector consists of maybe 1 million, maybe 10 million little things like this. When the light hits it, the electric charge jumps up here. In the CCD camera, it'll stay up there for a while. Maybe, may stay up there for 1/10 of a second. You take a picture in a 50th of a second, and you have all of these little individual elements, all these little pixels, these individual pixels, each one saying whether they were hit with light or not. Now they do something else in the digital cameras. In front of each pixel, they put a little filter. Let's see what colors I have here. In some of them, they'll put a green filter. This is the closest I have to green. In some of them, they'll put a red filter. And some they'll put, I guess that's blue, red, and I don't have green. Okay, they put these filters in front. So this pixel picks up only blue light. The blue light, only blue light will get through that filter. If it does get through that filter, then what it does is it takes an electron from the insulation band, knocks it up to the conduction band. It sits up there until the picture is all taken. Now what you have is each of these chips has a certain number of electrons in their conduction band. Depends on how much light there was. If there was a lot of red light, then this one will have a lot of electrons. If there was very little blue light, right here, this one will have very few. Now you've recorded the picture in electrons. Now the electronics comes around and it basically hooks up a switch to read out the number of electrons in each one, sends that off to the computer. That's how it works. And they have these filters to let through they have 3 different filters. Typically what they'll do on the back of a camera, I mean on the CCD, they have all these different pixels. Okay? And what they'll do is they'll have green, half of them will be green. Half of them. That's because that's the color that's most sensitive. The eye is most sensitive to green. So half of them will be green, even though I drew that in blue. 1/4 of them will be red. I'm going to do 1/4 of these red. I don't know, 1/4 of them are red. And then the other 1/4 are blue. And then the computer says, well, it was green here, and it was red here, and it was blue there, so this must be white, because the color, either that or it's the edge of the page. It has to mix these together and calculate it. When anybody here into photography, anybody here ever take an image and keep it in what's called the raw format? Okay, one. Okay, well, raw format basically means you actually get all of this information. You don't have to know that. What I want you to know about digital cameras is that it consists of a large number of little individual crystals. Actually, they're all made of one big crystal, but the crystal is divided up. These are called the pixels, P-I-X-E-L. Each pixel picks up light, typically red, green, or blue, and only red, green, or blue because it has a filter in it. It then uses the photoelectric effect to measure the intensity of the light. Basically, more light, more electrons. More electrons, more current when they read it out. And that's what they measure. So it's turning light into an electronic signal. And solar cells work the same way, except instead of trying to measure the light, you're trying to use the fact that these electrons are now in the conduction band, so they will conduct away. They can move, and you can read out, you can get electricity out of it. There are a lot of technology going on in solar cells. The trick right now on solar cells are 2 things. One is to make them efficient, so that when the light comes in, you get a large amount of light back. Typically, a cheap solar cell will give you like 15% of the incoming energy is turned into electric energy. For some of the really expensive ones using different crystals other than silicon, I think you can get like 25 or 30%. So that's one thing. The other is to make them really cheap. And that's the key. To make them cheap enough that you can spread them out over a large area and turn the sunlight, use the energy of the sunlight to create electricity. So, I have just talked about solar cells, digital cameras, and Xerox machines. Let's do a little bit on lasers. The original lasers closely related to maser. The maser got its name from microwave amplification by stimulated emission of radiation. First maser was done by Professor Charlie Towns, who's still a member of this physics department here. He got his Nobel Prize for it. He made, as near as I can tell, in his life, only one mistake. Microwaves, as you know, are a form of light. And he called it a maser instead of calling it a laser, because it is light. It's just a different frequency. His students were the first to do it not with microwaves, but with light, as opposed to microwaves. So now there are people who say, oh, Professor Townes didn't invent the laser, he only invented the maser. And the laser has become the more famous word, but in my mind, he invented the maser, laser, whatever. He wasn't the first to build something using visible light, but it's basically the same principle. But here is the way it works. It can be done with gas. It can be done with a solid. With a solid, like in my pocket laser here, it takes advantage of the energy gap again. Well, all lasers take advantage of the energy gap, but in the solid thing, it uses the band gap. It creates the same crystal we have here. Look, here's the diagram. Okay? And what we did for this over here, you shine light on this and an electron shoots up. The basic idea of the maser and the laser is to do this backwards. So what you do is you take this crystal and then you pump up the electrons. So normally this is full of electrons. Now what you do is you put a large number of them up here. You pump it. How do you pump it? Well, there are many ways to pump it. We use the word pump by analogy. You're taking the electrons that have low energy and giving them high energy, but there has to be a gap. Now, how do you pump them? Well, you could have electricity flow through. You don't want this thing to be completely filled. So this is a not filled. And you send electricity flowing through this. Through collisions, these electrons get bounced up to here. There are many other ways you could do it. You could actually do it by shining a bright light on it. Use the photoelectric effect. So you pump them. I want you to know that you have to pump them up. And it's less important to know that you can do this with electricity or with a bright light. And there are other ways to do it too. So you pump these electrons up, and now you have them in this state. Here they are sitting there. Well, why don't they fall back down? The answer is they will. I mean, it doesn't happen instantly. They have this higher energy, and at some point, there'll be an empty state down here, and they'll jump down to it, and they'll emit light. So when they come back down, they emit back out the energy that they had absorbed from your electricity or from your bright light source. So far, it sounds like we've gained nothing. Here's where we are. We have a crystal or a gas. We excite the crystal or the gas by getting energy above the energy gap. And then you wait. And if you wait, that electron will lose its energy and emit light. No, so what? Big deal. That just sounds like a phosphor. Now here's the trick, and this is what Professor Townes recognized. And a name comes in, a familiar name, something that we've heard earlier today, Mr. Einstein. When studying quantum mechanics, he realized there must be something going on, otherwise quantum mechanics would contradict itself. And so he came up, basically this is one of these great theoretical inventions to understand the data. What he realized was there must be something, he gave the name stimulated emission. If stimulated emission were really a key thing for you to know in this course, we would go through the derivation of it. This is typically done at a junior or senior level physics major course. But here, what you need to know is the following. If you have one of these situations where you have a large number of electrons that are excited and can lose energy, and one of them jumps down, it emits light. And here's the key. that light acts as a chain reaction. It was on a quiz last week. That light will trigger other electrons to jump down in exactly the same way. And so you wind up getting a lot of light coming out. Einstein figured this out theoretically, that once one atom drops and emits light, it will stimulate other electrons to drop and emit light too. This is called stimulated emission. Now you start with basically one photon, and goes a little way, it becomes 2. And then 4, 8, 16, 32, 64, 128, 256, 512, 1024, etc. The old chain reaction thing. By the time you've gotten up to, 70 steps, you've basically emitted every single electron that exists in this crystal. Now, the trouble is you run out at the side. So what Professor Towns did was he put a mirror over here and one over here. And then once one of these things went off, bing, 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 bing. But then it would come back, bing, 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 bing. Then it would come back, bing, 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 bing. And you'd get the chance to go up and completely de-excite every electron that had been up there. This is the principle of the laser. It's called light amplification or microwave amplification because your first light gets doubled and then quadrupled and then 8, 16, it's being amplified. And it's being amplified because of this effect of Einstein, the stimulated emission. Okay, so what's important to know here? We haven't got to it yet. Look, I want you to know the following. You take something like this where there's an energy gap, and under certain circumstances, you can use stimulated emission to take all the electrons that are in the excited state, have them dump all of their energy in a very short period of time into this light beam. Now, the really remarkable thing about this is what makes lasers super special now. Because, hey, fluorescent light bulbs, what do? You have ultraviolet light. It excites the phosphor, and the phosphor emits light. It seems like the same thing. You send electricity through here. It pumps up the electrons. They emit light. What's the big deal? Here's the big deal. Because of the fact that it's quantum mechanical stimulated emission, the second photon of light will have the identical frequency and the identical direction of the first one. That doesn't happen in a fluorescent bulb. And so will the third and the fourth and the fifth and the 2 to the 50th. They will all have exactly the same frequency and be moving in exactly the same direction. So this is the key. The most important thing I want you to know about lasers is the following. That by using stimulated emission, you get all of the energy coming out with the same frequency, and all the light is moving in the same direction. Those are two aspects that make lasers into something that is important. So, aspect number 1, same frequency. Number 2, same direction. By the way, there are fancy words for this. Anytime a physicist wants to confuse you, instead of saying they all come out at the same frequency, what he will say is the photons are coherent. In fact, frequently this is taught to physics majors without really teaching them what coherence means. And if you look at what coherence really means, it means basically they all have the same frequency. They all come out in the same direction. That turns out to be actually, for most applications, more important than this one. This one is important if you're sending signals using lasers. Let's say you're sending a laser signal through a fiber optics. The fact that they're all the same frequency means you really only have one frequency present in that beam. And small changes in that frequency can be used to send signals. Frequency modulation. So it's really helpful to have just one frequency. The fact that they're all in the same direction, sometimes that's given a fancy name too. It said they're spatially coherent. And for some reason in physics, we love to throw these terms at students without explaining what they really mean. And then the student goes away thinking they know something, but confused. Same frequency, same direction. let me talk about the applications of the fact that they're going in the same direction, because this is really why I have a laser pointer. It looks like the laser beam is not spreading very much. It does spread some because it is a wave, but it spreads much less than you would get. What did I do with my laser pointer? Put it in some pocket somewhere. The trouble with having too many pockets. Now, how can I demonstrate my laser pointer if I've lost my laser pointer? I guess what I do is I talk about it while secretly searching and seeing if I can locate where I stuffed it. And so this is the way it works in a laser pointer. Typically, if you have the sun up here and it's shining, and you try to focus it to a single point, there's a problem. This part of the sun, all of its light will focus over here. Very good. But this part of the sun, its light will focus over here. That's why we have an image of the sun. When you're trying to burn something with a big magnifying glass, you're making an image of the sun down there. You want the image to be really small because you want all that light to get into a small thing. But it's still an image of the sun. You cannot get it to a point. With a laser, you can. Why is that? Because you see, the light here from the sun isn't all going in the same direction. This light's going this way, this is going this way. But for a laser, you put a laser up here, and all the light's going in the same direction. So you focus that, and that will actually go to a point. It won't be an infinitesimally small point because the light is a wave, and you can't focus it to better than a wavelength. But a wavelength is like half a micron. You could focus a laser beam, in principle, to half a micron, to a spot that big. All of the energy of the laser goes to that tiny spot because the light's all going in the same direction. You can't do that with the sun. So your laser may be, my pocket laser, which I still haven't located, may be less powerful than a flashlight. But it's right at the threshold where it could damage your eye. The reason it's right at that threshold is that when you look at this laser, your eye will focus this light into a tiny spot. All of the energy of this laser will go to that one spot where it's so concentrated it can damage your eye. So the ability to concentrate the light of a laser comes about because it's all moving in the same direction. And this has led to more practical applications than just about anything else. Certainly more practical applications than the fact that it's all the same frequency. It's all the same frequency used for communications. The ability to focus into small spots means you could put a modest amount of energy into such a tiny spot that you can actually burn. Well, more than burn. They built a laser at Livermore, the size, well, it's somewhat bigger than Pimentel. As I recall, I've been in it, it might be about 3 or 4 Pimentels put together. It's all filled with glass that was turned into a giant laser. So imagine a laser 4 times the size of Pimentel Hall. Why would they do this? The goal was to recreate the conditions in the deep interior of the sun. In fact, that wasn't good enough. They wanted to make it hotter. The idea here was to have this entire laser building all emit light at the same time, and then focus that light on a little dot, just a few millimeters in size. So if you can imagine this enormous amount of energy all going to this little dot, it would heat it up to a temperature higher than the inside of the sun. The goal was to see if you can get a thermonuclear reaction going in just one little thing without having to have a whole hydrogen bomb. We can make thermonuclear reactions with a hydrogen bomb, but then you kind of lose your building. The idea here is to make the thermonuclear reaction go, but on a little, something the size of a BB. If you can do that, the energy that would come out from a thermonuclear reaction, it's 1,000,000 times more than chemical. So you'd have 1,000,000 times as much energy as you would get from a BB of TNT. Now that sounds like a lot, but it could be as small as the energy from a few kilograms of TNT. You could contain that in a container. That's like containing explosions in your automobile. When you explode gasoline, it drives a piston. Here you are making a thermonuclear reaction on something that's so small that the energy can be contained and used to drive an engine. This was the idea. Normally, thermonuclear energy works on the sun, works on the hydrogen bomb. Can you make a small hydrogen bomb? No. Reasons I didn't really explain, but first of all, you got to trigger it with a fission bomb, because that was the only way to do it. Now, there's another way. Use a laser. Well, true, it has to be a big laser, and you have to focus all that energy on just one thing. But the first step is to just do it once. The question is, did it work? Well, the initial experiments did work. I believe they did see evidence of fusion, not in a practical way. It wasn't meant to be practical. But I'm not even sure I remember right now, because the whole thing was how much. You get the fusion, certain gamma rays come out. How many gamma rays do they see? And I think I'm not really sure. The project is no longer going forth. Now they have a different project using similar lasers at Livermore, which is to try to simulate the effects. It's called the Advanced Ignition Facility. And it also is working on a similar thing. Ignition here means to ignite the thermonuclear fusion in a small thing by using lasers. The key aspect of the laser that's really important is not the fact that it's the same frequency, it's the fact that they come out in the same direction and therefore can be focused to a very small spot, so you get all of your energy coming in. You can even have it coming in one pulse. If you make a laser that instead of bouncing things back and forth, what happens is you laze here, you emit a photon, double, 4, 8, 16, 32, 64. But instead of reflecting it, you just put more glass and more glass. Then all that energy builds up, and it's all going in the same direction. You can have it coming in a very short pulse. You can deliver your energy in a very short pulse. That is sometimes called, that's one method of controlled thermonuclear fusion. I'll have to check and find out what the current status of this. So it's laser induced. And you get your high temperature by having an enormous amount of energy, and the key aspect is you can focus it to a small spot. Now, actually, both of these technologies, if you want to take the same frequency in the same direction and combine them into an ingenious little invention, you come up with something called the supermarket scanner. So let me say a few words about how the supermarket scanner works. They use a laser, like my little missing pocket laser. Where's my pocket laser? Too many pockets. These are what are called hidden cargo pants. And inside each pocket, there are 6 pockets. And in that way, see, someone my age isn't allowed to look cool by having cargo pants. So I have to have hidden cargo pants. So I have all the advantages of cargo pants without looking like I'm wearing cargo pants. I wear cargo pants. My colleagues say, oh, you actually use those pockets? And I say, yeah. Well, for example, oh, that's where it is. OK. So here we have our little laser. What's done at the supermarket is they use a laser. They use the laser for 2 reasons. One is you can have a very small beam. And it's hard to get a beam of light that narrow. It doesn't depend on how far away it is. See, that's pretty small even over there. It does depend a little bit because it is a wave and it does spread. But mostly by using lenses and the laser, I can get the beam to be quite small. And what they want to do with this thing then is read the barcode. So you're going to buy something, it's going to say what? Or something like that. So this is going to be your breakfast. And what they do is on this thing, they will have over here a little thing that has a bunch of lines on it. Some skinny and some wide like that. This is a marvelous invention. Now, at the supermarket, every time you check out, you'll see there's a little laser there. You'll recognize it's going to look like a laser. And what they do is they wiggle it in a pattern, but it's really wiggled a lot. They do this using a clever method using holograms, by the way, a spinning hologram. And they don't actually have to physically move this. They just spin a hologram in front of it. You don't, that's unimportant. What they do this, now here's what happens. This thing goes like this. Chocolate, sugar bombs. It doesn't understand it at all. It sees beep, boop, beep, 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 boop, beep, boop. It ignores that. Then it comes, it ignores everything. At some point, it comes down here and it goes beep, 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 beep. Gets a whole lot of beeps all together very quickly because these lines are close together and regular. It's looking for a beep, 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 beep signal. Now, if it goes this way, it goes beep, 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 beep. If it goes this way, it goes beep, 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 because it takes longer to cross the whole thing. But what it looks for is a pattern. It looks for a pattern of closely spaced pulses. And then it looks at that pattern and says, now I have found something. So it ignores this. Beep, boop, beep, beep. It ignores that. But here, beep, 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 it gets that. And now the computer says, we found the code. Now it looks at it to see how many lines are fat and how many are thin. Now, how does it see it? I've talked here about shining a laser on it. How does the computer see these things? Well, here's where it uses the frequency. Over here, you have a big lens, and all the light is coming over here on this detector, and it doesn't look, at any one point, it's looking at a given spot. But the trick is, you put a filter in here that lets through almost no light at all. Only light it lets through is the precise frequency of the laser. So they're room lights, and they have some green in them, but this one has a really bright green at a very particular frequency. You put a filter in there that cuts out all light except at that frequency, and then there's only one bright thing in the room, that's the laser. In fact, the laser bouncing off this will be brighter than the amount of green of this particular frequency that's in the lights. So that's the second trick. They use the frequency to simply detect the green light and nothing else. Well, there will be a little bit of green light from the lamps, but not much, and none of it's going beep, 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 beep. Now, the supermarket person, because these things are somewhat primitive, learns that it works a lot better if you take this thing and put this thing facing right at the laser. So they'll take it and they'll go like that. Different supermarkets will have different brands, and some of them work better than others. And in some places, they'll go zip, zip, and it'll come up on the board what it is you just bought. Total lack of privacy. Anybody can look and see what you're buying. Anyway, so it measures the light, and then the computer looks for the pattern. Once it's detected the pattern, then it looks to see the code. Short, short, fast, fast, short, fast, fast, short, fast, and so on. It's like a Morse code, and it usually reads the name of the item, not the price, because the price is not on the barcode. The price is in the computer. So it looks up the name of the item, and then it finds the right price. This is why if the price is labeled on this, you may still want to watch, because it could be they're charging you more. The label's on sale, but they haven't updated the computer, and that happens from time to time. So there we have sort of the most common application of lasers today. Of course, lasers are also used for eye surgery. And I've had surgery on my eyes for a detached retina, and I've also had LASIK surgery. In LASIK surgery, what they do is they shine the laser on the lens. Typically, they will do a little bit more. I mean, not gross you out, but the idea is you shine a laser. You could focus it very precisely on a tiny little part of the lens. You put so much energy there that this little part is basically vaporized away. And over here, it's not. So you can remove part of the lens, and then by going over the lens, you can reshape the lens by removing parts of the lens by using this energy. Lasers can be used to cut metal. Most famous example was in Goldfinger, the James Bond movie, where it's going to be used to cut some very sensitive flesh as well as metal. And they said, the interesting part of that story was Goldfinger says, shows him that this is an industrial laser. An industrial laser is cutting a piece of metal in half. And at the time when the movie was made, there were no industrial lasers that could cut metal in half. So, but this was only projecting 2 or 3 years into the future. And as I say, that's not hard to do. And now, in fact, there are industrial lasers that can do that. Laser surgery is used for other things, too. It has this nice effect. that you can cut very locally, and it heats things up. Surgeons for years have used hot knives because they tend to cauterize where they cut. They stop the flow of blood. So where are we now? Laser, coherent collimated. The book is full of other examples. Using a laser to clean a statue. A friend of mine did that, Walter Monk, down in San Diego. You have an old statue that's covered with dirt from being exposed to the pollution of the city of Rome for 2,000 years. You shine a laser on it. You could shine the laser so it heats. There are two things in the cleaning of the shadow of the statue. One of them is that you can focus it on the surface. The other thing is, once it's clean, it reflects the laser light. So you stop, it's only the dark stuff that gets vaporized. Laser weapons, people talk about boom, I got you. There's been talk of laser weapons for shooting down ballistic missiles. As they're coming in, you focus the energy on them. The Air Force has developed lasers to get above the atmosphere, which bends the beam and distorts it, tends to spread it out because the atmosphere has air, pockets of air that can bend the beam apart. It's like having micro lenses that bend different parts of the beam in different directions. You want to focus all the light on one spot. So you fly in an airplane to get as high as you can. You have mirrors that take this laser and focus it on the incoming missile. And then there are movies, they're probably on the web, that show this. You can do this at a distance, of 10 kilometers. And the light gets there instantly. Well, not instantly, it travels with the speed of light. But that's, in a millionth of a second. Basically, if you can see something, you can shoot it. And light gets there real fast. And so there are movies where they shot down airplanes using lasers. For the most part, the airplanes have to cooperate. Because you have to focus this energy on part of the airplane until it heats up enough. You're doing this from a great distance. You can't focus it to 1 micron. And so it's actually a lot harder to do than many people think. And essentially all of the demonstrations that have been done are with a cooperating airplane. There's a lot of debate in the arms control, military community right now on whether this will ever really be practical. There are many people who think it never will be, because if we ever do develop such a weapon, then the enemy will cover their equipment with mirrors. It's not going to shine back and kill us. It's just that unless the light is absorbed, it doesn't do any damage. So there is a real debate going on this now. Some people are still very enthusiastic about laser weapons because they're so fast, so precise, if you can see it, you can shoot it. Other people say the countermeasures are so simple that if we develop the enormous lasers we'd need to be able to do this, they can be pointed very quickly because you can point them with mirrors. Hey, sounds like a perfect weapon. But that they're easily countered. In fact, the weapons that have been used against missiles, if the missile just rotates as the laser beam is focused on it, then the heat doesn't all get on one spot. So there are counters to this, and that's the nature of the debate on laser weapons. I mentioned superconductors last time. Depending on the energy gap, let me just review what they do. If you have a bunch of electrons and they're, well, so there's some funny things about superconductors. The electrons tend to pair up with other electrons and move together in the crystal. This kind of behavior only happens at cold temperatures. There are no room temperature superconductors that we know of. It may happen at room temperature someday, and if it does happen, then it will really transform our technology, just like the airplane has transformed our technology. It'll be more important than the laser would ever be if we can get superconductors to work, because then we can send energy at low voltage over long distances with no trouble. It means we'll be able to build wind generators in the Midwest states, even though they're not near any of our cities, because transporting the energies from such long distances will be really easy. It'll mean we can use low voltages in our house. We could use 3 volts instead of 120 volts, because we're not worrying about the resistive losses inside the walls. So this really will transform if we ever get room temperature superconductors. Right now, the best we can do is things have to be cooled at least to liquid nitrogen temperatures. We understand why that's true. What we need is someone to invent a way to get around it. But at these low temperatures, what happens is the electrons all start moving together, and an energy gap develops. Now, if you're moving, you feel like you have no energy, and this is the way the analysis shows it works. If something hits you, actually what it's doing is slowing you down. But from the point of view of the moving electrons, you are picking up energy. Okay, so here I am, I'm moving along with all these other electrons, and now I hit something, bang, and go back that way. I'm actually losing energy, but from the moving point of view, I'm gaining energy, and in this moving point of view, there's an energy gap. And I can't lose little bits of energy. It has to be a big amount of energy. In a superconductor, the amount of energy that you get hit with, the amount of energy that you pick up in this moving reference frame is, for all practical purposes, below the energy gap, and therefore you don't collide. This is a weird thing of quantum mechanics. If you can't do it because you're not allowed to pick up that much energy, you don't. And so you don't collide because it's not allowed. Because you would have an energy that's forbidden. You'd have an energy where the wave cancels itself out. So what do I want you to know about superconductors? I want you to know they work because there's an energy gap at low temperatures in these things where the electrons can move together, and because of this gap, they can't lose the little bits of energy that normally add up to resistance. That superconductors are now used when you need to have large currents flowing for a long time. Typically, they're used if you want a strong magnet. For example, MRI. You need to be put in a strong magnetic field. You can have a strong magnetic field by having a lot of current flowing through wires, and they'll all heat up, and you'll use a lot of energy. But if you make it superconducting, you make the electricity flow in a circle, and you have it cool down enough so it just keeps on flowing. No more energy. Get it going. It just keeps on going. You have a really strong magnet based on superconductors. There was an accelerator that was going to be built in Texas called a superconducting supercollider. And again, it was going to use superconductors for its magnets and to keep and for all the current that flows in it, superconductors. So superconductors are one of these things that have been around now for a long time. And the main limitation is you have to keep the stuff cold. Because you have to keep it cold, it takes energy. It's energy. Typically, these things are cooled with liquid nitrogen in the so-called high-temperature superconductors, or liquid helium, which is very expensive for the low-temperature superconductors, and just creating that stuff. And it's warming up all the time because it's in contact with the outside world that's holding it in these containers. So the main energy use in superconductors is keeping it cold. It's like running a refrigerator. You have to use energy to run the refrigerator to keep it cold, but the superconductor itself doesn't use any energy. But it's based on the energy gap. Let me talk about the transistor now, because this is the heart of obviously I'm going to have to spill over into the next lecture on this. The transistor, we used to have things called transistor radios. Now they're called transistors. You carry them around and listen to music. They are basically things that take the very weak signal from the electric wave that's in the atmosphere and amplify it to the point where you can use it to run a speaker that you put in your ear. They are now all based on basically silicon chips. There's some others too, germanium. But they're based on the energy gap technology. So let me say a few words about transistors. Typically, a transistor works by taking two or more crystals, each one of which has bands. So here are the bands. And in this thing, a semiconductor, these are all filled, and this is the conduction band. Now, they do a trick in most transistors. They stick a few electrons up here. Electrons and positive charges, minuses and pluses. So there are a few up there. So you do get some electricity flowing. That's why it's called a semiconductor, because they do have a few up there. And over here, what they'll do is they'll put a few spaces down here. These things are called holes. So they make a few holes on this one. They do this by adding impurities. So it's a tricky thing that is the key to a huge technology. Now you just put these two things together, just like that, and an interesting thing happens. You just take this stuff is typically called N material because it has these extra electrons, negative charges. This thing is called a P material. And this is more detailed than you need to know. But some of you are curious anyway, especially if you've played with this stuff at all. You put N and P material together like this, and here you have some electrons over here, and here's some places where they could go. And so you wind up getting some of these electrons plopping down over here and filling some of these nearby holes. Just because they can lose energy, and once they've lost energy, there's no way to get it back. So you have electrons moving across here, and you wind up having extra electrons over here. This has extra electrons, extra E's. And this one has extra pluses, because the electrons left, but the positive charge didn't. Extra pluses. So you wind up having, this thing is called a diode. And if you put these two things together, you get some electrons moving across. It means you have extra charge over here and positive charge over there. You have a pretty strong electric field in between them. So just putting these two things together, you get an electric field. The result of this is if you try to make current flow this way, it'll be repelled by these electrons. It won't flow. But if you try to make it flow this way, it will, because it'll be attracted by these positive charges, and then it can move across. So this thing, if you put two of these together, you find that electricity can flow one way or the other. This is what's called a diode. And not too much I want you to know about diodes. What I want you to know is you can put together two silicon crystals in such a way that electricity will flow one way and not the other. That turns out to be enormously important for much of modern technology. Your power supplies for your computers, your transistor radios, and so on will take alternating current, let the current flow only one way so they could charge a battery. And we will go on with this and get to computers and amplifiers next time.